Hi dear students, today we discuss an experiment to determine the charge sensitiveness of ballistic galvanometer using a standard capacitor. We have already discussed the meaning of the charge sensitiveness of BG. Let me recall the definition of the charge sensitivity of BG once again here. There is a charge sensitivity is defined as the charge required to produce 1 millimeter deflection on a scale kept 1 meter away from the galvanometer. I request the viewers to watch the previous lecture first, where I have explained the working of a ballistic galvanometer with theory, and this lecture is a continuation of that previous lecture. So, to get a clear idea about the ballistic galvanometer, you first watch the previous lecture first. The deflection theta produced in the galvanometer, that is proportional to the amount of charge flowing through the BG. We have written this Q is equal to K theta, that is the K is equal to Q by theta. This K is the charge sensitivity of our ballistic galvanometer. This charge sensitivity can be defined in this way. This charge sensitivity is defined as the charge required to produce 1 millimeter deflection on a scale kept 1 meter away from the galvanometer. We have already defined the charge sensitivity of ballistic galvanometer in the last lecture. Now here our task is how experimentally this sensitivity of the BG can be determined. That is, this Q can be written as K theta, that is K into theta is nothing but theta 1 into 1 plus lambda by 2. This K is nothing but T by 2 pi, where T is a time period, C by N BA, then theta 1 into 1 plus lambda by 2. We have derived this expression in the last lecture. The whole quantity, that is T into C by 2 pi N BA, this is our K. Fine. Here I can write this K is nothing but T by 2 pi C by N BA. Here C is a non-capacitance. I will show you the experimental setup to measure the value of the K, that is a charge sensitivity. This is the experimental arrangement to determine the charge sensitiveness of BG, and this consists of a voltage source E and a key K1. It contains one more key also, that is K2, and this is our capacitor C, and here we have this arrangement, that is, this is the charging point, and this one is the discharging point, discharge, which means if the key is pressed or connected to charge, this charge knob, the capacitor will be charged. Similarly, if the key is connected to discharge knob, then the charge on the capacitor starts to decay, or the capacitor starts to discharge. Okay. Now this arrangement is these 4 plugs. This is a commutator. CR. CR means is nothing but commutator. Here this P and Q in this figure, these P and Q are the two resistance boxes from which you can choose the different value of the resistance. Now let me explain how the charge sensitiveness of Bg can be determined using this capacitor arrangement. That is, we know the expression that is for the charge on the capacitor, that is Q is equal to C into V. We are also having this expression. That is, if you come back here we have this expression Q is equal to K theta. Therefore, I can write this expression is equal to K theta, where this K is the charge sensitiveness of Bg. What is this V? This V is the potential difference across this capacitor. It's the potential difference. PD means potential difference across the capacitor C. If you look at this figure, here the potential difference across the C means once the key K1 and K2 are closed, then this circuit is now a closed circuit, this path, and the capacitor will be charged to its maximum value with the potential difference across this P. Here these two are the resistance boxes, and these resistance boxes act as a voltage divider circuit, and whatever the potential difference is come across this PD, that according to that potential difference or according to that voltage, this capacitor is charged. Fine. Therefore, this V is the potential difference across the C. Then we can write this V, that is this V, as if E is the applied voltage multiplied by the net resistance of this resistance arrangement, that will be P divided by P plus Q. You might have studied the voltage divider rule and voltage divider relation in the first year B.Sc physics course. Then with the voltage of V, our capacitor C is now fully charged. Or from this expression, I can write this K. K is equal to CV by theta. This CV divided by theta, we have the expression theta 1 into 1 plus lambda by 2. Now instead of this V, I substitute this expression. Then our K is equal to C divided by theta 1 into 1 plus lambda by 2. Instead of V, I substitute EP divided by P plus Q. Fine. Or I can write this expression K is equal to EC divided by P plus Q into P divided by theta 1 into 1 plus lambda by 2. This is the charge sensitiveness of Bg. Unit is micro coulomb per division. Fine. Now, what is this theta 1? What is this lambda? How it can be measured? That is our next target. Okay, and also using this experimental setup, how this k can be measured. Then, if you get the value of theta 1 and lambda, then you can find out the charge sensitiveness k of the ballistic galvanometer. For this, first we need to know the value of theta 1. Next, I will explain the procedure how to find out the value of theta 1. For this, let us go back to this picture. To find out the value of theta 1, first we close this key K1 and connect this K2, the second key, to the charge knob. Now you can see this is a closed circuit and the capacitor is charged with the potential difference across this P. Okay, let me write here, close K1 and K2. The capacitor is charged with the potential difference across P. Once the capacitor is fully charged, now we have to open the key K1. Key K1 is now opened and connect this K2 to the discharge knob. Our K2 is now connected to this discharge knob. Therefore, the charge on this capacitor, now see this part of the circuit is broken here, and now this circuit is fully connected. This is the commutator. Fine. You know the working of the commutator because you have already used this commutator in the laboratory. When the key K2 is connected to the discharge knob, the charge on the capacitor is discharged through this ballistic galvanometer. When a charge flows through this ballistic galvanometer, a throw theta 1 is noted. That is, this ballistic galvanometer registers a deflection theta 1 according to the charge that is flowing through this Bg. And this theta 1 is noted for a particular value of the resistance P and Q. Okay, let me note down this also here. Open K1 and connect K2 to discharge. Fine. The charge on the capacitor is discharged through Bg. That is a throw, that is a deflection theta 1 is noted. Throw theta 1 is noted. Fine. That is, for a particular value of the resistor, that is, we have the two resistors P and Q, and this is a P plus Q, and the throw according to the value of a different value of P and Q, you will get different value of deflection. Because if you see here in this picture, if you select the different value of P and Q, then the potential difference across the P will be changed. According to that potential difference, the capacitor will be charged. The charge on the capacitor, it depends upon the potential difference across the P and the and the value of the potential difference that depends upon the value of P also. Therefore, a particular amount of charge will be stored in this capacitor. When it discharges by pressing the key K2 to the discharge knob, then whatever the value of charge is stored here, accordingly the galvanometer that shows a diff. There is a capacitor discharges through the B.G. And if once again if you change the value of P and Q, the combination, then accordingly the potential difference across the C will be different. Then a different amount of charge will be stored in the capacitor. When connecting this key K to the discharge knob, then that charge will be discharged through this BG. Then another deflection theta 2 will be noted. Once again you choose different value of P and different value of Q. Condition is that total value should be constant in all the cases, and the potential, according to the potential difference across the C, particular amount of charge will be stored. Then that charge will be discharged through this BG when connecting this K2 to the discharge knob. Then you will get another deflection theta 3. This theta 1, theta 2, theta 3, etc. to theta 11 can be measured by choosing the different value of this P and Q. That is, here to measure the value of theta 1, first we select this combination, that is P is equal to 1000 ohm and Q is equal to 9000 ohm. The total is 10,000 ohm. The theta, that is, we note this throw in this case, that is theta 1. Another value of P, that is, if you select P is 2000 ohm and Q is 8000 ohm, then you will get P plus Q is constant, that is 10,000, and you will note the throw theta 2. And for different combination, if I choose P is equal to 3000 ohm and Q is 7000 ohm, this total will be 10,000, and the throw now is theta 3. In this way, for different value of P and Q, you will get different deflection, different throw. That is, finally I need to get theta 11. To find out the value of the Q from the experiment setup, E is applied voltage that we know, C is the known value of the capacitor, and P and Q are the resistance that we already know, and unknown factors were theta 1 and lambda. The theta 1 now we have found out from this observation. Next we need to know this lambda in this expression. How we can find out this lambda? That is, the value of lambda is obtained by observing first throw theta 1 and the 11th throw theta 11 using an expression. That expression we have already explained. It is 2.303 divided by 10 log theta 1 by theta 11. Okay. Let me note down that also here the value of lambda is obtained by observing first throw theta 1 and 11th throw theta 11 using the relation lambda is equal to 2.303 by 10 log theta 1 by theta 11. Okay, In this way, if you can find out the value of lambda, and if you know the value of lambda and theta 1, then you can easily find out the charge sensitiveness of Bg using this expression, because the value of E, C, P, Q are known already. This is the experiment to determine the charge sensitiveness of Bg using a standard capacitor. Okay, thank you very much.